What we did so far, I explained if you have a function, this function, a logic function that has 3 variables or 4 variables, I explained how can you simplify it using algebra manipulation and also using maps. So last time I finished 4 variables. And what we did so far in this chapter, I explained how to use the maps to calculate the simplified function in the form of SOP, sum of product. Okay? Now I'm going to explain if you want to get it in product of sum, what should you do? You will find it's going to be very similar to sum of product. You will see right now how you will do it. Let me tell you what is the main idea here. If I can calculate f prime in sum of product format, if I can calculate not f prime. Okay, if I can calculate f prime in sum of product format, and then I use De Morgan, I will get f in the format of product of sum. That's what I'm going to do. Different from what I did before, I'm going to calculate f prime, not f. Okay, similar to what we did before. So I will calculate f prime similar to what we did before, and I'm going to get f prime in sum of product format. And then, so if you, for example, if you have f prime equal to xy or x prime y prime, if you have something like that, okay? So if you take De Morgan, so this one becomes f equal x y or x prime y prime, everything inverted, okay? And as you know from De Morgan, this one should be x or y and x prime or y prime or x or y. Okay? I don't need to explain De Morgan again. We did it many times. So this is the main idea. If you have so if you have f prime in sum of product format, you can easily use De Morgan to get. So here I'm going to use De Morgan for the two sides. Okay. So if you invert f prime from f, if you invert this one using De Morgan, I'm going to get the function if in product of sum. Is that okay, guys? This is what I will do. So different from what I did before, I will calculate f prime, not f. But how can I do that? Very simple, very easy. I'm going to tell you how. Let me go back to any function we had before. Okay. Okay. So let me ask you a question. For example, if you have, this is the function f, right? And this is how I represented it. So in the logi, there is 1 here. So I'm going to put here 1. There is 0 here. So I'm going to put 0 here. You see what I'm saying? Okay. If you think about f prime, what's going to happen in f prime? Any 0 becomes 1. Any 1 becomes 0, right? So that means 1, 0, 1, 1, 1, 0, 0, 0, okay? And then 1, 1, and so on. F prime, okay? That means if I want to calculate the map of f prime, all what I have to do is anyone have to make it 0, any 0 I have to make 1. Okay, so that means this one should be 0, 0, 0, 0, 0, and everyone else should be 1s. So this will be the map for f prime. Make sense? Is that okay? Okay. In other words, what I will do is, and after that you can so here I'm gonna put here 1, 1, 1, 1. This one's anyone should become 0, and by this way, and after that I need to group the ones similar to what we did before. Nothing is new, but the function I will get is gonna become f prime. So now I create the map for f prime, okay, this way, and then the function I will get is f prime in sum of product. Okay? Okay, so we can do it quickly. Okay, we can do it without going through f prime. How we can do that? Look here, guys. If you have a map like this one, and similar to what we did before, if you group the ones, if I group the ones, I'm gonna get function f. But if I group the zeros, I will get function f prime. Why? Because these zeros should be ones in the map of f prime. You understand what I'm saying? So again, what I'm saying, we have two maps here. I have map that for f. In this map, I can use the same map for f prime, but you have to flip. Any one should be zero, any zero becomes one. So let me make it easy, very easy. So similar to what we did before, guys, if you have a map like this one, okay, if I group the ones, similar to what we did before, same thing as I did before, by this way, I'm gonna get f. But if you group the zeros, so here, for example, I'm gonna take these 4 zeros together, okay? If you group the zeros, or you can take these ones together, whatever the way you do it, okay? So here, if you group the zeros, in this case, you are gonna get f prime, okay? Why? Because the zeros should be ones in case of f prime, okay? That's exactly what I will do here. So what I'm gonna do is, guys, here's the difference between what I have already explained and what I'm going to explain right now. How can you calculate a function in product of sum? Okay, all what we have to do, exactly same thing as we did before. The only difference is, number one, you have to group zeros, not once. You have to cover all zeros, because keep in mind, these zeros are actually ones in the function of f prime. And then after that, what you are going to get is actually f prime in sum of product. After that, you need to calculate De Morgan to get f in product of sum. Is that clear? Okay, that's what I'm going to do right now. Okay. So similar to what we did before, number one, you need to cover all zeros. Similar to what we did before. Okay. You should not take any one. Only you have to take zeros. Again, I will repeat it again, because zeros now are ones for the function we are calculating, okay, which is f prime. Anyway, so let's see, for example, if you have something like this one here. Again, I'm not gonna work on ones as I said, so I can take these zeros together here as one group, and then I can take these 2 zeros together in one group. You have similar to what I said before. Number one, you need to cover all zeros. You need to maximize the size of groups. You need to minimize the number of groups, similar to what I explained before. You should not include any zero, any one in the groups. So I just flipped everything I said before. Okay, before when we calculate function f, you should not include any zero in groups. Here I'm doing the opposite. Once I do that, what I'm gonna get here, actually I'm gonna get f prime, not f. Okay, very easy. So if you group ones, if I group the ones as we did before, I will get function f in sum of product. But if I group zeros, so I'm gonna get f prime in sum of product. And then when you calculate De Morgan, I will get f in product of sum. I'm done. So that's exactly what I did here. So again, nothing here. The only difference, I'm gonna group zeros, not ones, and then I get f prime. Once you get f prime, you need to use De Morgan. After that, I can get f in product of sum. Any question? Let's see more examples here. So here, as you see here in this figure here, we have here, again, I'm grouping zeros. Okay, so all these zeros, one group. Nothing similar to what we did before. You need to maximize the groups. Exactly same thing. Once I do that, I get here, I'm gonna get this function. This function is f prime, not f, because I'm grouping zeros. De Morgan, once I use De Morgan, I can get f. In De Morgan, actually, I'm gonna invert the two sides. Invert this side and this side. Okay, because you know, if A equal to B, so for sure A prime is equal to B prime, right? That's what I'm doing. So I'm gonna calculate the prime for both sides, and then I use De Morgan. So here, f prime of prime is f, and then when I use De Morgan here, I'm gonna get the function f in product or sum. That's it. Any question? In test one, I will give you. It's gonna be 4 variables as I told you, and it may be sum of product or product of sum. Okay, so they are very close, almost the same. You got what I'm saying? So you need to know how for 4 variable for test one, for 4 variable, you need to know how can you calculate the simplified function of sum of product or product of sum. Okay? Also, it may also contain the last part here we have. I'm talking about this one, which is don't care. So let's talk about don't care. I already explained it before, but here I'm gonna repeat again. Okay. So what don't care means? I explained it before. Don't care means. Let me give you example. I wanna do something on. I have here a logic function, and the input here is actually BCD. You know, BCD means it's a binary number from 0 to 9. This is BCD. Okay. So how many inputs I can have? For sure, 3 inputs are not enough, because in case of 3 inputs, you can have number from 0 until 7. But here I have until 9. That's why the only option I have is actually 4 inputs. But 4 inputs are going to give you number from 0 to 15, which is more than what I need. Okay, more is going to be better if it is less than what you need. Okay, because I don't have the other option, either 3 or 4. Okay, 3 is going to be short. Okay, but because it's going to go only to 7, so I have to go for 4. Okay, that means so here this function should have 4 variables this way. So that means I can have numbers here from 0 to 15. But actually, the numbers from 10 to 15, you should not use them, because the correct input has to be a number from 0 to 9. Okay, the input should not, if it is correct, should not be number from 10 to 15. Okay, but what happens if I input 10? What can happen? What happens if I input 11? What happens if I input here any value from 10 to 15? What happens? Okay, what happens, because you have here gates, you will get something here at the output. Do you care if the output here is 0 or 1? You care? I don't care, because the input is wrong. So the output here, if it is 0 or 1, I don't care. You understand what I'm saying? That's why here it came the word don't care. That's why I explained this concept before, but you will see it here. That's why if you look at the truth table here, for example, for the numbers from 0 to 9, if this is the input, I need the output to be 0. If this is the input, the output has to be 0. If this is the input, the output has to be 1. But when I come to this number from 10 to 15, I'm going to say X, or sometimes we use D. Okay, X means I don't care. I don't care means if this is 0, okay. If you want to make it 1, it's not going to help me as well. You understand what I'm saying? So it doesn't matter for me if for this input, it doesn't matter for me if the output is 0 or 1. You understand what I'm saying? Because this input should not come. But if you put it, I don't care about what output you will, because you need to get some output. Okay? Because it's gates, you will get something. It's like you have an algorithm, and then you put wrong input, so you will get something. Okay. But what you are going to get here, I don't care if it is 0 or 1. Okay, this is the meaning of it. Now, and this is the most important thing. Okay, so how I can leverage this one, how I can use it for my interest. Okay, the way you can use it for your interest is, as long as it doesn't matter if it's 0 or 1. So all what I'm going to do is, if this one is going to help me to do more simplification, okay, I will make it 1. You understand? So now what we have to do here in now the key maps, so you should have zeros and they have 1s. Also they have X or D. X or D. It means we don't care. Okay. So what you have to do here, you need to cover all 1s. You don't need to cover X's. So you don't need to cover all X's. So as what I said before, you need to cover all 1s. Okay? So now the question is how I can benefit, how this don't care can help me. I'm going to tell you how. So if I don't, if in this specific problem, I can make a group this way. This is one group, okay? And this one can be also one group. I can make two groups this way, okay? But actually, I can simplify it more. You know how I can simplify it more? If this don't care, I can consider it one. So consider it one means I'm gonna output one when this input comes. I'm gonna output one, okay? If I can consider this one once, I instead of making group of two, I'm gonna make group of four. So this one here and this one. Okay. Okay. So here, this one I'm gonna consider it once. Same thing here. If I can, if instead of taking these two together, no, I can actually consider these ones as well as once. I can make bigger group. So the conclusion is number one. I'm repeating it. You don't need to cover all x. I don't care about x. If it's 0, 1, I don't care. So you don't need to cover all of them. Okay. Number two, you can use x to maximize the size of groups. Okay, by x can be 0 or 1. So try to use it for your benefit. Okay, whatever can help you to maximize the group. Okay. Any questions here? So all what I did, I took instead of taking this group this way and another group this way, no, I can make it group of 4 by considering don't care. So don't care can help me. Number one, you should understand the concept of don't care, what it means. Okay, don't care means I don't care. I don't care about the output. If the output is 1 or 0, I don't care because this input should not happen. Okay. Let me say it in a better way. So this function is not defined. This function is not defined for this input. Okay. This is number one. Number two, can help it. Don't care can help me to simplify it more as you will see in this example. Yes, your question or no? Yeah, for you. You raise your hand. I answered it. Let's see more examples here, guys. Let's see this example here. Okay, so for example, I have here don't care here. So by the way, I write it this way, and the question this one will have don't care. So it will have don't care, and it would be 4 variable. Okay, so it should be written this way. So this is the location of once. This is the location of don't care. Okay, so all what I have to do in this location, I have to put 1. So in location number 1, number 5 is here, 3 is here, 5 is here, 7 is here, 9 is here. So these are the location of ones. This one here are the location of don't care. So number 6. In 6, I'm gonna put x. In number 12, I will put x. In number 13, I'm gonna put x. Is that okay? Now let's see how can you do simplification. Okay, it's very clear. I can take these 4 together. Okay. I cannot make group of 8, but I can make 4 here, right? So this 4 can be taken together. Okay. Yeah. So here this is one group. The second, now what is left? What is left is only this one. What is left is this one here. Okay. So now I have 2 options. Either I take this one alone this way, or I can benefit or I can make use of this don't here. I can consider this one like 1. If I can do that, so this becomes one group. So instead of making one group of 1 square, I can make one group of 4 square. That means in this case, I'm gonna output 1 here for this input, and I don't care if it's 0 or 1. Again, you don't need to cover all x. You don't need, okay? Because I don't care about x. 0 or 1. Any questions? That's why the better solution here is just to take. So look, you should understand. Look how don't care helped me. Instead of making group of only 1 here, I'm gonna make group of 4. Okay? Let's have more examples to show you. For example, if you have yeah, so for example, let's have this example here. If I don't take advantage of don't care, look how I will do it. I can take this 4 together, and then I can take these 2 together. You will get this function. Okay. But actually, if you take advantage of don't care, instead of making group of 2, I can actually make group of 4. I can actually make group of 4 by considering this x is 1. So any x you can flip it 1 if this can help in simplification. You don't need to cover all x's. Okay, you have to cover all ones. Okay? Same thing if you want to calculate a product of sum and you need to cover all zeros, same thing. So x here, any x you can consider it 0 if this can help you to do more simplification. So without simplification or without taking advantage of don't care, this is the function I'm gonna get here. But if you take advantage of don't care, you are gonna get more simplified function. So the two functions here have 2 terms. Okay. But this term here is actually only 2 variables. This one actually 3 variables because this is group of 2 and this one group of 4. Any questions? Yeah, so here I give you also one more example here. I want to build a logic circuit that determines if a decimal digit is greater than 5 or not. So that means I have here 4 inputs. So here I have 4 inputs, 1, 2, 3, 4, and I have 1 output. Okay. If the input is greater than or equal 5, for example, I'm going to get 1. Otherwise, I'm going to get 0. Okay. This is function greater than or equal 5. Okay. So let's do the truth table here. So for the truth table, when the input is 0, the output has to be 0. Okay. And the input here is 1. Okay. And the output is 0 until 4 it is 0. But when it is in this range, when the input is greater than 5, greater than or equal to 5, the output has to be 1. One more thing here is the input here has to be BCD. BCD input means it's a decimal number from 0 to 9. That is why here I'm just from 10 to 15. I'm going to say don't care because the input has to be BCD, has to be from 0 to 9. Okay. Okay. So I will have a truth table like this one. So again, all what I'm going to do, guys, in these locations, I'm going to put zeros in the map. In these locations, I'm going to put ones in the maps. In this location, I'm going to put X or I put 0 in the map. Okay? I don't need to cover all X's or all these. I don't need to cover them. However, if any X, I can flip it 1 or you can flip it 0 if this will help you to do simplification. And that's what I'm going to do here right now. Look how it is really very interesting here. So if you look here, for example, here, if you don't use don't care, I would only take these 2 together. Make sense? If I don't take advantage of don't care, I'm gonna take these two together. But I can make group of 8 by taking all of this here. So this way, I'm gonna consider all of these. Is that okay? So now, for sure, if you have a group of 8, it is more simplified than having group of 2. Make sense? This is number 1. Number 2, same thing here. Without here, I would take these 2 together, and then I would take these 2 together without here. Okay, but I can make them bigger. How we can make them bigger? I can make 4 this way, and then another 4 this way. I think the last example I have here, the last example I have for variable here is actually for POS, product of sum. Okay. So here I give you the locations. Here I give you the locations of the zeros. So every time you see bar, so these are the locations of zeros, and these are the location of don't care. So the first thing you have to do, so in this location you have to put zeros, okay, and in this location you have to put X or put Z, don't care. Okay? So here that's how I represented it this way. And now I wanna, so for sure the other location should be ones, but I don't need to write it, but should be ones because it's either 0 or 1 or X, don't care. So these are the location of don't care. These are the location of zeros. Other location should be ones. Okay. So anyway, so now similar to what I explained before, you need to group the zeros. You need to group the zeros, and also you can take advantage of the don't care. Okay. So here, in order to group the zeros, so it's very clear if I can consider this don't care zero and this don't care zero, I can make very big group of 8, okay, which is actually x prime. Otherwise, if you don't do that, it would be the best option for you just to make here group of 2, and then another group of 4, and then another group of 4. Okay, so I'm gonna have 2 groups, and everyone 4. Okay, but by taking advantage of don't care, I created only one group, and this group is actually 8, much better. Anyway, and for the I need to cover all zeros, as you know, so I can take these four zeros together. This actually is going to give you W1. Okay, so this is f of prime. Then after I get f of prime, I can calculate f this way. Any question? Same thing, if in case of 3 variable, nothing is new in case of 3 variables. So here, as you see, I can take these 4 together, okay? And then I can take these 2 together. You don't need to cover this one. You don't need to cover it because it's not required to cover x's. What I have to do here, I have to cover all ones. Okay? So here, I'm gonna output 1 here. So when you implement this circuit this way, so you here in this case you are gonna output 1, but for this one you are gonna output zeros. Okay? Anything that's outside the groups, you are gonna output 0. Anything that's inside the groups, you are gonna output 1 here in this case. So here, if you don't care, this is how it's. This is the function with don't care. This is the function without don't care. I just want to show you how don't care can help me to do simplification. So instead, here I have to take this one alone instead of taking 2. That's what I did here. Okay. Same thing. I need to make group of 2. Okay, but don't care. I can make group of 4. Okay. So in the test 1, I will give you something like this one here. It's going to be for variables. I will ask you to, it will don't care. I will ask you to write the simplified function either in sum product or product or sum. Any questions? Okay. The title of this chapter is actually combinational logic circuits. As I told you in the beginning of this course, the purpose of this course is not to teach a computer system, but I will teach the basic devices that we use to create a computer. Okay, these basic devices, and that's what I'm going to do in this chapter and also in the chapters. So I'm going to use what I did before regarding algebra manipulation, regarding key maps, and then design devices. That these devices are doing something, and these devices can be used to create a computer system. So as you see here, first of all, I'm going to make a definition. This chapter is about combinational circuits. Okay. I will make a definition. What do you mean by this one? And then after that, I will teach different devices here we use, like BCD to excess3 code converter, a binary adder and subtractor, multiplier, comparator, decoder, encoder, multiplexer, demultiplexer. Okay. So let's start here with the definition. Combinational circuit versus sequential circuit. So we can divide the logic circuits into combinational or sequential circuits. Okay. In chapter 5, I'm going to teach sequential circuits, but in this chapter here, I'm going to teach combinational circuits. So you don't need to worry about sequential circuits. That's what I'm going to teach in next chapter. But here I'm going to just make a definition. What is the difference between everything we have done in this course is actually combination. So combination circuit means the output here, the output of the circuit depends only on the input. That means every time for the same input, I will get the same output. That's what this is the definition of combination. And that's actually everything we have done so far. For the same input, I will get the same output. Okay. However, as you will see in next chapter, in case of sequential circuits, we have something like a memory element. In other words, okay. So the output does not only depend on the input, but also depend on the current state. So if I'm in a certain state, okay, and I get an input, okay, a certain input, I will get a certain output, okay. But in the state, for the same input, you may get different output. This is the main difference. Okay, but anyway, you don't need to worry much about this one because this is the topic of the next chapter anyway. But the main difference between combinational and sequential circuit is, in case of combinational, the output I'm gonna get only depends on what is the input. Okay, but here the output depends on two things, not one thing. It depends on the input and what is the current state. Because it may be for the same input, I will get different output if we have a different state. And this is state related to memory, something related to what was the input last time. But anyway, so you don't need to worry about this one because that's what I'm going to teach. But so now in this chapter, I'm going to teach combinational circuits. And that's everything we have done so far. So you don't need to worry. Everything we have done so far, the output only depends on the input. Okay. So how can we design a circuit here? Okay, it's very simple. For example, we have already done this one. Okay, so if I want to do something, how can we design it? For example, as I explained before, if I wanna design a combinational circuit, this combinational circuit, for example, it has 3 inputs and it has 1 output. I'm gonna call it the majority. I already explained it before, the majority circuit. So I wanna design a circuit that gives me output if the majority here is 1. Sorry, if the output gives me 1, if the majority is 1, and gives me 0 if the majority is 0. I wanna design a circuit to do something like that. Okay, so what should I do? Number one, you have to create the truth table. Okay, so here you have X, Y, Z. You have to put all possible inputs here. So as we did before, and then 1, 2, 3, 4, and then 0, 0, 1, 1, 0, 0, 1, 1, and then 0, 1, 0, 1, 0, 1, 0, 1. And then I have to define what is F. I have to define what is the output. Okay. So here in this case, because this one is a majority, so here the majority is 0, so the output has to be 0. The majority is 0, the output has to be 0, 0. Here the majority is 1 because I have 2 ones and 1 0. Here the majority is 0, majority is 1, majority is 1, majority is 1. I define the output. Okay, this is the first step. So the first step, that's what we have done. Okay, nothing is new. And then after that, you need to use key maps to do simplification, and then you can get f after that. So f is going to be function, f is going to equal whatever x, y, or whatever function in x and y after you do simplification. Is that okay? That's what you have to do. Yes. Also, that's what we will do in this chapter as well. You will see how can we do it same way. However, as you will see, okay, what is the problem? Think about any problem we have here. Is this approach can work to design any circuit? Any circuit that just use this approach? Why? Simply because there is a very weak point here. What is the weak point? The number of possible cases is actually equal to the power of n, and n is the number of variables. So if you have too many variables, the table is going to be very unstable. It's not going to be practical to do it this way. You got what I'm saying? So I can say this approach is okay as long as you have a reasonable number of inputs. Okay. But for example, if I have just an example, if I want to multiply 8-bit number by 8-bit number, look how many possible. So now I want to multiply or add 8-bit number to an 8-bit number. Look how many inputs I will have. 16 bits. 16. So it should be 2 to the power of 16, which is going to be like big. So anyway, I think it's going to be 65,536, something like that. That is why in such cases, usually we are not going to do it this way. So most of the time, or again, if the number of inputs are reasonable, okay, I will design it this way. But actually, you will see in this chapter, sometimes I'm not going to do this way, but I need to do some tricks, okay, to make the design more efficient. Okay? So in the first part here in this chapter, I will use this approach. For example, here, let's start with the first one here. I want to create a circuit. This circuit BC2 to XS3 code converter. So this circuit is going to be a converter. It has to convert from one code to another code. Okay? The first code we call it BCD. This is the input. So this is the input of this circuit is actually BCD. The output is XS3. So you input a code, you convert it to another code. Okay? So let's see what is BCD. As I told you before, BCD is actually a binary number from 0 to 9. So this is 0, 1, 2, 3, 4 until 9. This is the input BCD. Okay. We have another code here. We call it XS3. In XS3 code, actually, what happens? You need to add 3. So 0 here, 0 should be 3. 1 should be 4. So every number you add 3. There is a reason for that, but this is how the code is. The code is if I want to represent the number 0, so I'm going to use 1100. So 1100 is actually 0. Instead of using 000 as 0, so for number 0 should be 3. Okay? So everything shifted by 3. There is a reason, but this is how it works here. So this is how this code works. That's why it's called XS3. Okay, so you can see here this one is number 1. This one is actually number 4. So 4 is actually number 1, right? Anyway, so when I want to represent the number 1, I will use this one. Okay, and so on. So if you see here, this is number 9. 9. This is 12. Okay. Anyway, so again, I have 2 codes to represent the numbers. You understand what I'm saying? So to represent the numbers, I have 2 codes. I can use, for example, number 0. I can represent it like 0, 0, 0, 0, or I can represent 1, 1, 0, 0. I'm going to represent 0 this way if this is actually XS3. I'm going to represent 0 this way if you are using BCD code. So this is code, this is another code. So now what I'm going to do right now is I want to do a converter. So here I want to design a circuit that can do conversion. The input here is BCD and the output should be XS3 code. Okay. Why this converter is useful? Okay, assume you have a system and system is using BCD, and you have another system that use XS3. And I want to connect these two systems together without changing the systems. All what I have to do here when I connect it, I'm going to put the converter here. So the converter will do like a translator. Someone is speaking English, someone is speaking Chinese or Spanish or any other language. I need someone in the middle to translate. That's exactly what happens here. So here, say I can do a converter here so that this converter can take the output of this circuit, which is BCD, to convert it to XS3. Okay, for sure you can do converter in the other way if you want. Okay, but here I will focus on how can you do converter from BCD to XS3. When you go home, you can try to do the opposite. Okay, so how can you do that? Number one, now I have a truth table here. This is a truth table here. If this is the input, this should be this is the output. This is the input, should be the output. This is the input, this is the output. Okay. You can see something interesting here we didn't do before. Okay. All the truth table we had before, in the output, you have only one output. If only one output. But this time you have 4 outputs. You know what I'm saying? This is the difference. This is something we didn't do before. So we had 4 inputs before, but for the output, we used to have only one output. But this time we have 4. There is no problem because every one here is going to be a separate function. So you can see it like this one is a separate function. Okay, this one is a separate function, separate function, separate function. You understand what I'm saying? So it's like you have 4 truth tables. So that means I have to do KMF for this one, and I have to find what is the relation between W and EBCD to get one function. Then I have to do this one and so on. So I think I have a nice figure here. Yeah, so here you can consider this one like F1, F2, F3, F4. I want to see what is the, how I can get F1 as a function in ABCD. Okay, so this is how the circuit should look like, as you see. The circuit, you should have like I need a function here F1 given ABCD. I'm gonna get W. You understand what I'm saying? So again, what I'm saying here, this is for the first time you see a truth table that has more than one output. Okay, but there is no big difference because what this is, I'm gonna do exactly everything as we did before, but every output is gonna be like a separate function, Okay, so that means I need to have four maps, one map here, one map here, one map. Anyway, okay, guys. Okay, so and then how can you design this one? Very easy, very trivial. So now you have this is the input, and you have don't care, and also this is the output. Okay, I can make here. I have to make 4 maps, as you see here. H1 here, for example, for Z is the last one here. This is Z. I have to put here, as you see here, I have to put the location of ones. I have to put the X don't care. We have don't care here because the input here is up to 9. Anything from 10 to 15 is don't care. Okay, so I have to do that, and then I have to do group. So once here it's easy. I have only one group. So Z should equal D prime. So the function Z only depends on D. So A, B, C has no impact on. Z. Z is equal to D prime. And even if you look here, if you compare Z with D, you find it is prime. Okay, for example, when this one is 0 here, this one is 1. When this one is 1, this is 0, flip. Okay? You can notice it here. Everything is here. Okay, okay. I'm done with Z. You have to read everything again to Y. So here for Y, again, for Y, these are the location of ones. I'm going to put the location of ones here. I put it here. And then I have here don't care. So here now I'm going to make one group here and another group here. And this is Y. So Y equals CD or C prime D prime. So the value of Y is actually depends only on C. It does not C and D. It does not depend on A. Okay. You remember this function? This is a very well-known function. There are 2 important functions you should memorize, guys. Can anyone tell me what is this? Yes. No, you raised your hand. You need to answer.
Answer comment.
Yes. Exclusive, no. Okay. So there is two functions you should know because we are going to use them, guys. These two functions are actually, if you have here x prime y or y or x y, x y prime. So one with prime, the other one without prime. One, and then you switch them this way. So this is actually x exclusive or y. Okay? There's another one here, which is xy or x prime y prime. So I put every inversion on one side without inversion on the other side. Okay? So this is actually x exclusive nor y. Okay? And actually, this one is the inversion of this one. So here, this is exclusive nor is actually exclusive or inverted. So if you invert this one, you get this one. If you invert this one, you get this one. So they are inversion to each other. Okay. And regarding functionality, as I told you before, this is equal. This one is actually don't equal, which means this one will give you 1 when the two inputs are equal, 0, 0 or 1, 1. This one don't equal. So this one I would give you 1 when the two inputs are not equal, 1, 0 or 0, 1 when they are not equal. Okay, these are two important functions. Anyway, so here, yeah, this is the function I got here. Same thing. I need to go for x, do same thing for x. So here I'm gonna, as you see here, I did it like four separate functions. 4 separate. They are separate. Okay? So here, same thing. I have to put the ones, and I have to simplify it. You have not here. So I got x this way. Finally, I got nothing is new. And then after that, see here, this is the circuit I can get based on what I did so far. This is the circuit I can have here. So using this circuit here, the input here is BCD, the output here is XS. The second part here, circuit here, and it's binary other or subtractor. So how can you do addition? Someone asked this question earlier in this course. So how can you use the logic gates we know to do addition and subtraction? Let's start. I'm gonna start with the first one here. We'll call it half other. You will understand why you call it half, but half other. So half other is a circuit that can actually add so half other. So I'm gonna start with the first one here. We'll call it half other. So half other, it can only add 1 bit to 1 bit. So here I have a circuit. This circuit I have a circuit. This circuit has 1 bit input, 2 bits, 1 bit to 1 bit. Here x and y, and I want to add this bit to this bit. Okay. The output here should be the summation and also carry, because there may be a carry as well. When you add two numbers, like 1 plus 1 is 0, and there is a carry. Okay, so the output should be summation and the carry. Here in this first, we call it half other. So half other is a circuit that can add 1 bit to 1 bit, 2 bits, 1 bit to 1 bit. Okay? This is the interesting part. I will start with something very simple. You add bit to bit, and then you will see how I can grow it to add. If you want to add
1 million bits, 1 million bits.
You will see how I will grow it. But I will start with something very simple. I'm going to add 1 bit to 1 bit. Okay? So to do that, as you see here, again, I will make a truth table, and then I will get a function. Okay. This is too simple because you don't need to make maps here. This is too small. You have only 2. You can even do it using algebra manipulation. Too small. So here, as you see here, guys, 0 plus 0. The summation is 0 and carry is 0. There is no carry. 0 plus 1. The summation is 1. Carry is 0. 1 plus 0 is 1, and then we have 0 here. 1 plus 1 is 0, and then we have 2. And then here you can use some of you remember this is the last quiz we had. So here how can you get here? How can you get the function here without maps? Okay, I can make it in min terms. So this one here, carry should equal x and y. But this is the only case, x and y. Okay. Same thing, summation. So I need to get the min term for this one and the min term of this one. Okay. The min term for this one is actually x prime y, so x prime y, and for this one here is actually xy prime. So this is similar to what we did in the last. You don't need maps here because that's too simple. Okay, that means this is how I can implement this function here. You can, for sure, you know this function is actually
xy prime
or x prime y. You know this function?
Okay.
So the way I can implement this function, what I can put here in this box here, what I can put here is actually, as you see here, xy prime or x prime y. You can make it this way, or as you know, this is exclusive or. So s here is actually x exclusive or y. Okay, that's what I did here. As you see here, s is actually x exclusive or y. C is x and y. So this is small circuit, very small circuit. It has only 2 gates. So this is small circuit can do addition for 2 bits. Add 1 bit lower. Any question? Again, I'm gonna start from something very simple at 1 bit, and then you will see how I draw it up easily. Any question? Is that okay? Now, what if I want to add, for example, 2 bits to 2 bits, or I want to add 10 bits, 100 bit to 100 bit, for example? Can I use a truth table like this one? For sure, it will be too complicated. That's what I told you, right? If you want to add 100 bit, 100 bit, that means you need a truth table that has 200 inputs. How many records you are going to have? 2 to the power of 200. This is very huge number. For sure, it's not going to be efficient to do this. It's not going to be efficient. I'm going to do a trick. What is the trick? I will tell you what is the trick. So it's a trick. So you are going to have too many cases, too many inputs. So I'm not going to do this way. So I'm going to do a trick. So what is the trick? I will tell you. So the trick here, I'm going to design something. I call it full adder. You remember this one, we call it half adder. When you add just 1 bit to 1 bit, we call it half adder. But here, when you add 3 bits, I call it full adder. So I'm going to add 3 bits, and then as a result, I have summation and carry. So what is the trick you want to make? I'm going to tell you what is the trick. Look here, guys. And why you want to make this full adder? Okay, I'm going to tell you. Look here, guys. If you have a number, for example, I have here A0, A1, A2, A3. This is number A. If I have another number, number B, which is actually B0, B1, B2, B3. Is that okay? When I add them together, should be A0 plus B0 should equal S0. And then if there is a carry, A0 is here. If there is a carry resulted from this operation, this carry has to come to here. And now I have to add 3 now. I have to add 3. So, and then I have here S1, and if carry carry C1 has to come here. Okay, same thing here. I'm gonna have S3, and then I will have a carry here. Okay. So if I want, that means I need to add 3 bits. Why you need to add 3 bits? Because I'm gonna add 1 bit to 1 bit, and then maybe a carry coming. I need to add it as well. That is why I'm gonna create a full adder. So the full adder is actually gonna have three inputs. Okay, and it has 2 outputs: summation and carry. And what I can do is I can use full adder for each one of this one. Oh, how? I'm going to tell you how. This is a big picture. So instead of making one, this is a trick I told you. Instead of making one table, okay, I'm gonna do it this way. Look here, guys. In the very beginning, I can in the very case I can use half adder. I'm gonna input here A0 and A1, and then I'm gonna get S0, and the carry here, the carry should be input to the next phase full adder. So here I'm gonna use half other. I can use half other in the first one, but here I'm going to use full other. Okay, and this full other, the output is summation is here. Carry, the carry has to go to the next one here. Okay, so here I'm going to use full other. The carry will come here, and then also I'm going to input here. I'm sorry, I think I made this. This one should be A0 and B0. This one should be A1, B1. And because of this full other, I'm going to have here the summation, and then I have a carry. This carry can go to the next phase as well. So here, and then here I have A2, B2. Same thing here for other, and then here I'm going to get a summation, and there is a carry. It's going to go to next one. Here, what I did here, guys, to understand the general idea here, everyone here needs full other, one full other. And the carry resulted from this operation is going to be input here.
The carry input next one.
Now,
If I want to add 1 billion bits to 1 billion bits,
it's easy or difficult?
it's easy. How many others I need?
1 billion. So this is the beauty of this one. Every time you just add full, every time you add 1 bit, I need to add full other, and so on. The number of full others here. By the way, so it should equal to, so every time if you want to add more bits, so every time you want to add 1 more bits here, I'm going to add one more full other. Okay, so it's easy to expand it, very easy to expand it. Okay, for sure, this is much better than making a truth table, and this truth table has many record, and then you are, even after you do it, you will get functions that are maybe too complicated. So here I did a trick. You understand what I did here? Okay, so as you see here, guys, that is why I need to design full other. Full other is a circuit that can add 3 inputs together. Because these 3 inputs is actually 2 inputs plus carry. That's why it becomes 3. So I need to design a circuit. I have already designed half other. But here, in order to implement something like that, I need to design a full other. So now the question, how I can design it. Okay? So it's going to become very interesting. One block, okay, and then you repeat it. And connect output to input, output to input. So now, again, what I'm number 1, you should understand what is full other. Full other is a logic circuit. This logic circuit has 3 inputs or 3 bits, and then the output is summation and carry. This is full other. Also, you should understand why I need to design full other. I need to design it because what I explained here, in order to add 2 numbers together, I have to for every bit here, okay, I need for every 2 bits here, I need to use full other because there is a carry coming here, carry from here, and so on. Okay, so now let's focus on designing full other. Again, this is a logic circuit that has 3 inputs, 3 bits, and the output is summation and carry. So I'm going to use the traditional way. The traditional way you use it. I'm going to create a table this way. Here I'm going to put all possible cases for inputs, all possible cases, and then here the carry and the summation. 0 plus 0 plus 0. What is the result? 0 plus 0 plus 0 is 0. Summation is 0, and carry is 0. 0 plus 0 plus 1. Summation is 1, carry is 0. 0 plus 1 plus 0, 1 and 0. 1 plus 1 plus 0 is actually 0, and we have carry. 0 plus 0 plus 1 is 1. 1 plus 0 plus 1 is actually 0, and we have carry. Okay? 0 plus, anyway, so 1 plus 1 plus 1 is actually 1, and we have carry. So now we created the truth table for full other. And then after that, I can, for this one here, I can make a function to make, here I can simplify it to get the value of S and the value of C. So this is S, and this is nothing is new. This is similar to what we did before. Anyway, I think that's enough because we have a quiz. Exam is too easy. Shouldn't take more than 2 minutes. Don't forget to write your name. So this is the majority function. You did last semester. You did last quiz. Okay, but here I want to simplify it. Some of the proofs that correct.